Uh, Hello, Arjun. Can you hear me?
Yes, I can hear you.
Hey, thanks for joining. Thanks for
Let's
hosting.
let's start the recording. Welcome to Papers We Love 2, the San Francisco chapter of the Papers We Love conference. We hold this meeting on the second Thursday of every month. So naturally, we haven't held one since 2019. But the plan is to actually hold it on the second Thursday of every month going forward. Typically, our structure is that we have a mini talk that is 15 minutes and a long talk that is 45 minutes. Today, we only have the long talk, but the meeting is still scheduled for 2 hours. So we're going to have the long talk, and then we're going to have questions, and then we're going to have time for sort of group discussions that may be about the paper or sort of inspired by the paper. And then I want to reserve some time for discussing who should be on the program committee so that we can get back into a good flow of holding this meeting each month. The meetings are going to be recorded. So if you do not want your face on that recording on YouTube, then don't turn on your camera. And if you do not want your voice on that recording on YouTube, then don't unmute yourself and speak. We will be paying attention to the chat. So if you have any questions but do not want to be on camera or on voice, feel free to drop your questions in chat and I will read them out when we're having the question and answering period. Arjun, do you prefer questions all at the end, or are you happy to be interrupted if someone has a question as you go?
I think we can have it in breaks. So I have sections, so we can then have it after each section.
All right, so you can inject a question or two at a section break, but we will have questions at the end also. And with that, I can pass on to Arjun, who will be presenting WiscKey. This is a paper that I first encountered several years ago, and I think is a very good example of every time our computer systems get a million times faster, or a million times more storage, or a million times more bandwidth, maybe it's worth going back and rethinking things. If the time it takes to drive across the country went from 5 days to 5 milliseconds, I would change some of the ways that I plan how I do my travel. In similar fashion, our computers, when they get a million times faster or a million times larger in some dimension, I think it is worth going back and rethinking data structures that we've been using for years. And I think this is a good paper as an example of that. Sometimes it's worth going back and rethinking your structure. Arjun has been working on databases, and we are hoping he will give us insights not just into this paper, but how this paper may have effects on the kinds of systems that people actually need to build. This is a very practical paper made for practical systems that do stuff. This is not high abstract theory. This is you're building stuff and it should work fast and it should work reliably. With that, I will pass to Arjun. Thank you for presenting at Papers We Love.
All right. Thank you so much, Aaron. Thank you for the introduction. All right. So about myself, I'm Arjun. I work for a database company called Arjun. These days, I'm working on AI-related functionality for the database. Today, I am here to present on the paper WiscKey, separating key from value in SSD-conscious storage. It's authored by Langmu, Tanumalan, and two other people from University of Wisconsin-Madison. So this is the agenda so far. We'll talk about the motivation and use case for this paper. Then we'll go into the introduction, a couple of things to know before we read the paper, like what is LSM-tree, what is read and write amplification, how is SSD different from HDD, and then we'll go into the meat of the paper, which is the key idea. We'll talk about how each of the data flow happens, and then we'll talk about some challenges, and then we'll probably go into some of the variants of this paper, which was implemented by Couchbase, ByteDance, and so on. So yeah, Uh, as Aaron was mentioning, storage has evolved a lot during the past decade. So we had like initially we had some sort of a floppy disk and stuff like that. And around 1950s, we had the initial development of hard disk. Hard disk was a spinning disk based storage solution. And probably after the dot-com bubble and stuff like that, the data volume increased quite a lot so that it was not able to vertically scale the storage solutions. So we went into something like a distributed storage solution and things like that. Around 2008, people, especially uh, university uh, university-based academic work and industry work, kind of tried exploring RAM to be the primary storage for a database. Though RAM was not that expensive, was not that affordable, there was plenty of good research work on having main memory databases. Around 2011 was when SSD came out. SSD was not that fast as RAM, but it was not that slow as hard disk. So it offered its own benefits, but it had its own problems as well. Around 2017, we had PMM coming into picture from Intel, and I guess in the recent years they have discontinued PMM. And in the very recent year, we have this upcoming thing called as CXL, which kind of helps in disaggregated memory and stuff like that. So for each of the storage solution, we tailor-made data structures uh, utilizing the pros and cons of the particular storage device. So in the case of hard disk, especially we design every data structure, which was main memory, like binary SSD or anything of that sort, as block-based data structure. So B-tree is nothing but a block-based data structure of a sorted tree. And it had its own advantages, but like for write throughput, we developed a new data structure called LSM-tree. And similarly, for the distributed file system, uh, we had this cap theorem coming up, and it kind of uh, gave an insight that we can only have one or two among the three properties, which is consistency, availability, and partitioning. So based on that, there were mainly two types of databases, which was master-slave and slave-slave model. Cassandra chose to have slave-slave model, whereas MongoDB chose to have master-slave model. Talking about RAM-based systems, I think cache is one good example where main memory was used for a key value-based system. There were other systems which wanted to use RAM, but yeah, they uh, utilized RAM for a scenario where keys were smaller in size when compared to value. So keys would reside in the main memory, and then values would reside in the storage solution like hard disk. So with that approach, they were able to have a hybrid storage solution for main memory databases. And for SSD, uh, there was no specific optimization done for LSM trees running on SSD. So around 2017, WiscKey came out, and that's the paper that we are going to discuss today. So the motivation behind the paper is that LSM tree had large read and write amplification when the value size is very large. And LSM-tree, the then LSM-tree was not optimized for hard disk, and the paper, WiscKey paper, tries to address both these things. So let's see. When we typically have large values, let's say image or a PDF or a document, what we do is we write the document or an image into an object store like S3, and then have the URL or the metadata information stored in the database. In this way, we don't increase the size of the database, and we are safe with the file getting stored in the object store. But in the modern era, we have new use cases where we prefer to store JSON and JSON as a data type in the database. So we have large JSON stored as blob in the database. And also in this times, we can see that every other database is now introducing vector type as first-class citizen into the database. So vector is nothing but an array with a float 32 type. So let's say OpenAI has vector embeddings which has dimensions from 1000 to 3000, I guess. So if we multiply 1000 with 4 bytes of float 32, we'll have 4K sized values. So we see that large values in databases are possible. And in this era, I think with this use case is pretty much possible, and we should probably have a storage engine which can manage large values. So with that being said, we'll go into the introduction of LSM-tree. Typically, key value storage are classified as B-tree-based or LSM-tree-based. We have a few companies which have their own storage engines written in either B-tree or LSM-tree-based data structure. So the fundamental difference between B-tree-based and LSM-tree-based storage engines is in place versus out of place updates. So in the case of so on the left side, we have a single data structure, which is, let's say, B-tree based solution. And on the right side, we have something which is out of place update data structure. So typically, it's a collection of data structure. In the case of LSM-tree, we have it as multiple SSDs and things like that. We'll go into the details in the upcoming slides. And yeah, in the case of out of place update data structure, we typically store key along with the timestamp so that we keep version related information in the database. So let's say we want to delete an element from the in place data structure. What we do is we traverse from root to the node and then we delete the element. So in this traversal, there could be scenarios where we might need coarse-grained lock or fine-grained lock on individual nodes. Okay, so for this reason, there can be large lock contention, and it could result in slower insert or delete performance. In the case of out-of-place data structure, typically a delete would require you to add or append a value saying that append a tombstone value saying that the value is deleted. This way, the data structure insert and updates are really fast, but it becomes a problem when we do a read. So in the case of a read, we can see if for reading 12, we can probably do the same root to node traversal and see that 12 is not present, so we can immediately return the result. But in the case of an out-of-place data structure, we have to do merge on read, which involves reading data from all the individual data structure. So this adds latency to the read process. So that's why we say that LSM-tree is mostly optimized for writes and B-tree is mostly optimized for reads. That being said, let's talk about the main components of LSM-tree. We have memtable or immutable memtable, which resides in the memory. And we have write ahead log, and we have something like levels in the disk. So memtable is the initial buffer where all the writes are written. When memtable reaches a specific threshold, it gets swapped into immutable memtable and is still kept in the memory. When time comes in, it is pushed on to the levels, which is in the disk, and then we have some sort of a compaction going on. So yeah, here we'll go over three major operations of an LSM tree. We have writes. So we write key and value into the write ahead log first because we want to make sure that writes are durable. After we write into the write ahead log, we write into mem table, and then we write we write into mem table. When mem table reaches a specific threshold, it gets wrapped in as immutable mem table. And then when immutable mem table kind of the list of immutable mem table kind of gets full, we write the immutable mem tables into the level 0 of LSM tree. Level 0 is the place where you can have key overlaps, meaning that SSD1 and SSD2 can have keys which can be overlapping with one another. Now we'll go over compaction process. So in the case of compaction, what we do is we typically pick two SSD files and then we merge the SSDs and then we write it to the next level. In this process, we make sure that the SSDs in the level 0, level 1 to L7 are not having overlapping keys. This way, during the read process, we only need to probably hit one SSD and do some binary search to find the key and all those things. So only in L0 we have this key overlap, but in L7, L1 to L7, we don't have key overlaps between SSD. That being said, we'll now go into the read operation. So typically, when we want to read the value, as I was talking about out of place data structures, we want to do merge only. So first thing that we do is we query both mem table and immutable mem table and see if the value is there or not. If the value is not there, we start querying from all the levels in L0 to L7. So for L0, as I was mentioning, since keys can have overlap, we'll query all the files in L0. But for other things, we probably will find the first file which has the key, and then we'll only query that file from that particular level. To improve the performance for disk accesses, we can maintain a Bloom filter in the main memory so that we can do a initial lookup in the Bloom filter to see if the key is present or not. Now we'll just quickly compare how SSD differs from hard disk. So SSD was based out of flash memory chips, whereas hard disk was based out of magnetic platters on a rotating disk. So since it involved rotation, random reads were slower due to seek time, and in the case of SSD, random reads are lately faster as there is no rotating disk. Also, the read-write performance difference was like around 100 Mbps for HDD and 500 Mbps for SSD. One of the major drawbacks of SSD was that there was only limited write cycles for SSD. Just like a battery of phone, we have some sort of a life cycle, write cycles, a fixed set of write cycles, after which the performance kind of degrades for SSD. That was not the case for hard disk. And one more thing is that typically when we want to do a deletion on SSD or HDD, typically when you want to do a deletion on hard disk, you can soft delete and then overwrite on the soft deleted data block later. But in the case of flash disk, you must erase the soft deleted data block before writing new data into that particular segment. So that means, apparently this process of erasing soft deleted data is performed by a garbage collection within the SSD. And if you have a lot of fragmentation in the SSD, the garbage collection can have a major impact on the SSD performance. So for this reason, it is not good to do a random writes. And the same goes with hard disk as full, because when we do random writes, we need to seek to a particular location, and that adds latency. And yeah, in this slide, we'll talk about what is write amplification. So write amplification is the amount of rewrites or amount of physical data which is written to the storage medium for the same set of logical data which you need, which you intended to write. So in the case of LSM tree, due to a step called compaction, we write data from level 0 to level 1 and so on until the final level. In this process, you may rewrite the data multiple times, resulting in higher write amplification for LSM tree. So why is it bad? It's bad because it reduces the write throughput of LSM tree, and as compaction sometimes interferes with the active writes, foreground IO of LSM trees. And the second problem is that typically, as I was telling, SSDs have limited write cycles. So if you are rewriting it a couple of times, then it probably wears out the SSD earlier. So this is the number. This is like a number from one of the slides of WiscKey, where it says that if we are writing 500 GB of user data per day to an SSD, the SSD can last for around 1.5 years, 1.25 years. Read amplification is the amount of data read, which is more than like for a particular key, it is the number of data you need to read to get the actual value. So in the case of LSM tree, since we do a merge on read, we have to have we have to read from all the set of individual data structure, which adds on to the read amplification. So this means that single read application, single read operation may require reading multiple data blocks or files to retrieve the most recent version of the requested key. Okay, so we have seen the terms which are required as a prerequisite to read the paper. Now we'll see what are the problems with current LSM tree. One of the biggest problem with current LSM tree was that it is having high read and write amplification. So this is an example where we load 100 GB data into the database and we issue 100K lookups, random lookups. So you can see in the case of write, the amplification ratio was almost 14, and in the case of reads, the amplification ratio was almost 327. This number is not good when the value size is very large and you are doing multiple rewrites on levels, smaller levels than larger levels. The second issue was that it was not optimized for the SSD. So typically in the case of LSM tree, level DB, which was particularly targeting, which was initially targeting hard disk. As you can see, when a key is requested, it sequentially hits all the files rather than parallelly hitting all the files. So this kind of was a bottleneck in the case of hard disk, but it was never a bottleneck in the case of SSD. So this WiscKey paper talks about how we can parallelly query all the files and make the best use of SSD. Before we go further, are there any questions? Okay, I think I'll go further. So the key design goals of WiscKey was to reduce read and write amplification to make sure that the LSM tree is optimized for SSD by leveraging sequential writes and parallel random reads, and making sure that like all the current APIs like get, put, delete, scan, and snapshot was supported in the new design, and having a realistic key value size. So, like in the case of values, we can have larger values as well rather than just smaller values. So the
When they
main
say
idea was
realistic key value sizes, do they mean that they're just very unbalanced? Keys tend to be much, much smaller than values.
uh, yeah. So in the initial slides, I was mentioning about use case where JSON and vector can be stored as data types in the key value store, right? So so the original LSM tree did not really give any consideration for value size, and due to that reason, like we had high write amplification. In this thing, what they are saying is that okay, let's say we have smaller size, and we should also think about larger value size, which is like 128 KB or something of that sort, and that's also possible. So yeah, I believe that's what they are saying. Like typically keys are really small when compared to the value, but yeah. Cool. The main idea of this paper was to separate out key from the value. So the simple approach was to have key, and so the simple approach was to pair key along with the address and value stored in a separate thing called as value log. So okay, let me just repeat this one more time. So let's say we have key and value. Right now in the original LSM tree, key and value was stored in one uh, single LSM tree. But from here on, WiscKey suggested that key would be stored in the LSM tree along with the address, and value would be stored in something called as value log. So this way, we are uh, this was the main idea of this paper. Okay, this improves write performance of the application and helped in reducing the SSD lifecycle by requiring only fewer erase cycles and stuff like that. So here we take a simple example on how this symbol change can help you benefit uh, reducing the write amplification. So the example has 16-bit key and 1 KB value. So in the LSM-tree-based, regular LSM-tree-based approach, uh, let's say if we have the write amplification as 10, then we would be doing the total writes of 10 into 16 plus 1 or 1024, which would mean that like write amplification is actually 10. But in the case of WiscKey, as I was telling, only keys are getting stored in the LSM tree. So the write amplification of 10 would be only applied for the key, which is 16 byte long. So it would be like 10 into 16 plus the 1024, which is for the value. So in this way, we can see that the write amplification or the number of rewrites gets reduced by a drastic amount. So what exactly do I mean by the numbers? What exactly do we see in the numbers? So here we are inserting 100 GB data into the LSM tree. Okay. So in the case of level DB, each of the level, including level 0 to L6, has these many files. Okay. It has 9 files in L0, 30 files in L1, etc., etc. But in the case of WiscKey, since we are only storing keys which are very less in size, we have number of files reduced in each of the levels. And you can see that it is only having up to level 3. It is only having files up to level 3. So this small LSM tree structure helps in reducing, helps in having lesser compaction cycles and fewer levels to search, overall improving both write amplification and read amplification. This can be seen in the graph which compares level DB and WiscKey. So here we are loading 100 GB data into both level DB and WiscKey. As you can see on the x-axis, we have the value size, which is ranging from 16 bytes to until 256 KB. And on the y-axis, we have throughput, which is Mbps, which is like the throughput of insert. So in the case of level DB, you can see that the graph is pretty much constant. It's not giving that much of a throughput when the value or size increases. But in the case of WiscKey, you can see that throughput increases when the value increases, because the total number of the total write amplification in this WiscKey based approach would be very less. So due to this particular reason, we have higher throughputs because there are less compaction cycles and stuff like that. So we are able to insert much more data in the WiscKey based approach. Now coming to the lookup. So here we have a graph which compares 100K lookups on randomly loaded 100 GB data, which was from the previous slide. So since the LSM tree size in WiscKey is relatively smaller when compared to the original LSM tree size, we have faster or better lookup performance, because we only need to hit fewer levels as shown here, and also fewer files. So the overall smaller LSM tree aids to the performance improvement by reducing both read and write amplification. Now we'll go into the design and challenges associated with this symbol modification, which was suggested by WiscKey. So this would be the write flow. So in the case of WiscKey, when we write a key value pair, the first thing that we do is we write key value pair into the value log. Okay. So as you can see, ideally value should only be stored in the value log, but in this case, we are writing both key and value into the value log. This is for a particular reason, mainly to optimize compaction process, which will be covered in the later slides. Okay. So what we need to understand is that we will be storing both key and value into the value log. And then we can follow the normal flow of LSM tree, which is to write key and value pointer to the write ahead log, and then update the mem table with key and value pointer, and then rest of the flow is similar to what we have seen in the LSM tree, which is mem table gets swapped into immutable mem table, then immutable mem table gets written into L0, and so on and so forth. In the case of a delete, we don't need to update value log immediately. We just update the key stating that the value is deleted. So in the case of writing nil, it means that we are writing tombstone entry to the particular key. So we update the write ahead log, and then we update end table and so on and so forth. In the case of reads, it's kind of a little different from the earlier LSM tree, because now when we do a read, we probably need to read the value from the value log, and that is expensive because like right now you want to, it's kind of increasing the total number of read operation within the SSD. One of the proposed solution from WiscKey was to maintain was to do parallel reads. So as I was telling, SSD supports parallel reads, and the original LSM tree was not optimized for leveraging parallel reads, but in the case of WiscKey, they uh, they were focused on the benefits that SSD would give, which was supporting parallel random reads. So also we could prefetch the values from the value log so that each of the okay, sorry. So yeah, what we do is in the case of reads, we issue parallel reads to as all the levels, and then we fetch the corresponding value log in separate threads. Okay, uh, corresponding value from the value log in separate threads. We maintain some sort of buffer, and this buffer will be responsible for keeping a particular, let's say, the next 10 elements, including key and the actual value in the main memory. So by doing this, we are actually making the best use of SSDs, parallel SSD support for parallel random reads, and we are kind of mitigating the issue which we had when we would go with the flow where we would read the key and then we need to go to the value log to read the value. Now we'll talk about how compaction is done. So since we have separated both key and value in the case of WiscKey, keys compaction is relatively straightforward since keys are stored in LSM-tree. So in the case of keys, we'll follow the similar compaction strategy which was used in the case of LSM-tree. In the case of value compaction, it's a little bit different or a little bit tricky. Here we have a simple scenario which uh, shows value log and LSM-tree. And here we have like 4 inputs. Okay, we have put of key 1, key 2, key 3, and then key 2 again. So in the LSM-tree, we have all the 3 values, all the values. And in the value log, you can see that we have the corresponding key K1 V1, K2 V2, K3 V3, and K2 V22. Okay. So what happens is, okay, head is the place where writes to the value log happen. Okay. So whenever we want to write value into the value log, we'll be writing it on the head. And tail is the place where compaction happens. So when we want to reclaim the space, tail would be the part where we start doing the garbage collection. So the approach that WiscKey took is we would do something like we pick elements from the tail and we check whether the value address that is maintained in the LSM-tree still points to the value address that that's stored in the value log. So this is the time where storing key in the value log makes sense. So we'll pick the first element. So in this case, we'll pick this element K1 P1, and we'll check whether K1 is holding the same address one, which was the one that's stored in the value log. So if K1's address is similar to what is originally there, then it means that it's still valid. But in the case of K2, we see that address is no longer valid because K2 has a newer value, which is V22. So that can be removed from the value log. So what we do is we reinsert the key value to the head, the valid key values to the head. So all the previously invalid values will be deleted and all the newer values will be updated into the value log again. So this way, LSM-tree maintains the newer value log address, and we can reclaim the values which are no longer being pointed from the LSM-tree. In practical implementation, this is what it would look like. We have value log, which is a collection of blocks. Okay, So each vlog is kind of representing a fixed size block which has 13 key values. And if you zoom into the value log, internally it will have KV pairs. We check whether the value pointer for the particular key is still valid in the value log. If it is still valid, then we make sure that the values, the key and the value pair is maintained in the new vlog block. And later on, we update that vlog into the value log. So if in this scenario, you might ask what happens. So if you reinsert the value log and previously if the value was being deleted, will that be a problem? So when we are doing a reinsertion, we make sure that we use the older timestamp which value log was maintaining. And in this way, when we do the parallel scan on all the levels, the latest version, if it is being deleted, will be showing as deleted rather than being impacted by the recent value log insert.
If you have very few deletes, isn't this going to cause more write amplification?
Could you repeat the question? If you have very few deletes,
the stuff that has not been deleted gets moved from the back of the value log to the front of the value log. Isn't that
correct.
creating more write amplification?
Yeah, that kind of makes sense. Yeah, I'll probably talk about the papers which came after WiscKey, which were addressing this issues, similar issues. Okay.
Thank you.
Yeah, as you were mentioning, that could also add up to the value right amplification. Also, since we are checking LSM tree for the existence of a key, it also adds up to bottlenecking the LSM tree index. So we'll discuss in later improvements of WiscKey paper. We'll talk about these things. Okay, so one of the concerns that we might have with this key value separation is the crash consistency. What happens if we crash the servers before value was written? What happens if we crash the service before key was written? How would we handle this? So one of the property that's offered by the modern file systems like ext4 is that it is not possible for random bytes to be written at, uh, at the file end. So by that, what I mean is, let's say if the file contains b1 to bn, and if you are trying to append bn plus 1 to bn plus m, and if a crash happens, you will have values from b1 to bn, and then bn plus 1 to n plus x, where x is always less than n. In verbal terms, what it means is if a value x in the value log is lost in a crash, all the further values are also lost. You won't have corrupted values written in the value log. So coming back to the original question, original issue of crash consistency, what happens when value is not, before writing the value to the value log, if we crash? In that scenario, it's totally fine because we haven't written value into the value log, as writing value into the value log is the main entry point for our put operation. Second is what happens when we write value into the value log, but before writing data into the key LSM tree, our database crashed. In this scenario, we don't need to worry about anything because this value will be removed from the value log at later point because there is no valid key which points to the value which is stored in the value log. So that's totally fine. And third scenario is when we have value in the value log and corresponding key in the LSM tree, can there be a method where value is no longer valid when we do the query? So for this particular scenario, whenever we read a value from the value log, we can verify whether the key that is attached to the value is still the same as the key that you have it in the LSM tree. So also you can maybe add a checksum or something to verify that value is not tampered or anything of that sort. But yeah, overall the crash consistency is not an issue with this key value separation. Some of the further optimizations that WiscKey paper suggested was to have value log buffer. So this is not applicable for synchronous inserts because it involves buffering writes in the memory, and then when the memory dedicated memory page or block is full, you do an fsync. So in this process, it is optimized for writes, but you have some sort of a crash inconsistency because if you crash before fsync, then you might lose the data in the memory. During lookups, we would check value log buffer first and then hit the disk. So that's one change that was suggested. And second was to reuse value log as write ahead log. If you look at both write ahead log and value log, it's kind of doing the similar responsibility, or like it's kind of in a similar access pattern. So both write ahead log and value log are sequential access patterns. So we can kind of use value log as a replacement for write ahead log. One of the changes that was proposed in the paper was to record head of value log periodically in the LSM tree as key value pair. So in this case, we can have a keyword called head and then corresponding value pointer, which is kind of maintaining checkpointing of the current value log head. And during recovery, it can read from the head pointer to the current end of the value log and recreate the state in memory. Okay. After, like ever since the WiscKey paper was released in 2017. Okay. Before we go further, are there any questions on WiscKey paper? Okay, cool.
Do they talk about when to acknowledge writes?
Sorry.
You probably don't want to acknowledge a write happened when it's just in memory. You want it to be flushed to disk, but that's going to slow down your performance a lot. Versus just acknowledging the writes once they're in memory and assuming that the write ahead log got them.
Yeah, so this value log buffer, I think this is just one paragraph where they talk about further optimization, but I am assuming that if we are having value log buffer, then probably it's safer to have write ahead log in a synchronous fashion where we flush it to the disk and make sure that it's durable. But yeah, it comes with the cost. Like if it probably shouldn't be acknowledging it. I don't know. Like if you're sure that there won't be any crash, then you can use this mode to kind of optimize your writes. But yeah, if there is a
so
crash,
trade-offs
then
for the application to decide.
yes. Okay. So ever since WiscKey came out in 2017, there were a couple of variants of WiscKey. In the recent years, I was reading about Magma. Magma is a storage engine paper from Couchbase. So it has all the components of LSM-tree and WiscKey. So here we have active mem table, and then we have immutable mem table. Oh, sorry. And we have immutable mem table, and writes are written to index LSM-tree. So this key index LSM-tree is maintaining key and probably the value pointer. And then we have writes going into the log structured object store. This is nothing but value log. So yeah, this part is kind of similar to what we have seen so far in the WiscKey paper. The only difference is that they are maintaining something called as delete list LSM tree. So this is an optimization where they optimize the garbage collection for value logs. So uh, so during compaction, when we merge two SSDs, uh, we do a deduplication step. So in that deduplication step, the older versions which needs to be deleted uh, are having some sort of a callback function where after the compaction process is completed, you write those older values value pointer in this delete LSM tree list. Okay, so once uh, okay, so when you store delete LSM tree list, essentially you are maintaining information or statistics about the number of uh, stale entries in the value log. As I was telling, each value log or vlog would be some sort of a block, and within the block you will have key value pairs. And if you kind of superimpose the delete list on top of the value log, you can have statistic information like the number of fragmentation in a particular vlog and things like that. So in this case, here we can see that there are three vlogs, and each vlog has corresponding fragmentation ratio. So in the case of fragmentation, uh, so yeah, this statistic information can be used for doing better compaction. So we could pick up uh, vlogs which are having higher fragmentation ratio, which means higher fragmentation ratio means that more stale documents. So we probably can merge those vlogs, and yeah, we can merge those vlogs into a newer version and then rewrite it back into the value log. So this way, we make sure that any compaction that occurs in the value log makes the best use of the statistics information provided, and we reduce the number of compactions in the value log. So thereby reducing write amplification issue in the value logs. Aaron, I think this is one approach where yeah, using stat information can reduce the write amplification on value logs. The second,
It's always nice when you're worried about something and the solution is 3 slides later.
yeah, it's been out there for a while, right? The paper. So a couple of other companies have optimized it fair enough for their use cases. So yeah, cool. So Terra from ByteDance is another database which optimized WiscKey paper. So in the case of Terra, what they did is instead of maintaining value in a value log, they maintained value in a dedicated LSM tree, or not directly an LSM tree, but they call it as VSSD. Okay, so VSSD is kind of similar to the SSDs, but yeah, uh, instead of maintaining it as a log, they use some sort of an LSM tree approach for the value log itself. So one of the major changes with this approach is that what gets stored in the LSM tree for keys. So in the case of LSM tree, in the case of items that are getting stored in the LSM tree, it would be key and the file number. So this file number, which is let's say if VSSD1 is having file number 1, then the value which will be getting stored is going to be the file number. Okay. So one of the advantages that you have with this approach is during compaction. So when you do compaction on SSD, when you do compaction on value logs, you essentially merge two VSSDs. Okay, so you pick two VSSD, then you uh, check if it's still there in the LSM tree, and if it is not there, you write it into the VSSD, write it as a new record in the VSSD. When you do this right, the only change, so yeah, previously what happens was that when you write into the value log, you have to update the LSM tree with the new address for the particular value. But in this approach, what we do is we maintain some sort of a mapping where each file has corresponding, each file ID has corresponding file location or something of that sort. So when we do the merge and when we rewrite into the VSSD, we only update the metadata information about the file location. So the original LSM tree will be having the previous file location, and when during the read time, when it want to read the particular file from the value log, it will access a metadata table which has file ID and file location information, and based on that, it will fetch the corresponding file. So in this way, we are essentially reducing the number of writes that happens in LSM tree during a rewrite process or value log compaction. So there are quite a lot of other LSM tree variants as well in this particular blog, but I haven't covered all of them. But yeah, these two are something that I found interesting. And with that, that concludes my talk on WiscKey paper. Any questions so far? All right, thank you. And awesome.
Yeah, thanks for doing that.
Cool. Thank you.
Let me move Spotlight and move to a more open discussion. So it seems like both WiscKey and a lot of the follow-ons was really driven by we now have SSDs. Do you think we need to rethink these things more now that we tend to have very large amounts of RAM cache available in these servers?
Right.
Like, are there other things that you would say if you were rethinking the LSM tree today, you might want to do slightly differently than the way, say, Magma did them or Tarek did them?
Yeah. So I think one of the recent advanced work that is happening is CXL. So CXL is an approach where you can pool memory from multiple servers and show it as one large memory block. Thereby, like, you can make use of that memory block as, let's say, a page server or some sort of a cache or like all those kind of things. So that is one interesting research direction. But yeah, CXL has its own pros and cons, like just like any other storage solution. So yeah, I think CXL is one thing that I'm looking forward to. And yeah, there are quite a lot of other papers which came out recently on disaggregated memory data structures, like designing data structures like B-tree, extendable hashing, and all those things, specifically for this kind of a disaggregated data structure. Yeah. All right.
I was definitely thinking about that last version where it's like, oh, we have these sets of sorted string tables that we then compact and have different chunks that are getting compacted independently. And that's making my brain jump to the, well, if I want to provide durability, for years and years, the standard of practice was have 3 copies of every SS table.
Mm-hmm.
And now more and more people are like, how about I have 1.4 copies where I have 10 of these tables and then 4 parity blocks that will let me recover
Yeah.
the raw tables.
Yeah,
Right.
there's
I feel like
a
doing it today, it's much more interesting than just having the straight levels to say, oh, I'm going to break this into a bunch of chunks so that then I can have a durability group and then have just the parity blocks.
there's a data warehouse called Ocient that uses error correcting code, or parity or whatever you want to call it. And yeah, they did exactly that. Not three times, but like 1 point whatever to get to for very large scale. They were trying to do really like petabyte, exabyte kind of stuff. So your storage cost is worth more than like the entire company. So,
Yeah, I mean, so when I was back working at Twitter, when it was Twitter, we were doing 3-way replication, and Facebook had their Hadoop patch for doing 1.4 replication. And we just changed a config, and it freed up 20 petabytes of data in one of our systems. And it was just like, well, that was convenient. Like,
yeah, we paid
it's
for
always
like
nice when Facebook just shows up and's like, here.
yeah, we looked at the triplicate and Vertica only needs like a duplicate, and we looked at the storage cost of that and justified like a big huge Vertica license with it, just because the triplicate storage was it's a lot. It's just not the best. Yeah, I'm trying to think. I don't. That was pretty clear though. I don't really have any questions. Since I haven't been here in a while, I think you were saying we haven't had one of these in a while. Is that correct?
Yeah.
October 22nd, 2019.
Yeah, that's a few years. Okay.
There's
I
been
think
a
it's
couple other
coincidence.
places have
Yeah.
done I'm from Seattle, and we've had a
Okay.
couple
Well, yeah,
here, but yeah, it's been a pretty hit and miss.
I think it was just luck that I checked in and signed up for it a month or two ago. And then, it happened to be the first one in that much time. I thought you might
But
have
we're going to
lost.
do it again
Yeah,
every
like,
second Thursday.
okay, I just want to make sure we don't, lose track of this, because I'd like to keep coming and doing this and helping out if I can,
Awesome.
And some of those old event spaces are open again. Like I went to GitHub the other day, last week, I don't know, for something, just some event, meetup thing. So they're definitely functional if you ever want to have a meet space meeting. They might be interested.
Yeah, so I haven't talked to the in-place places yet. My guess is that we're probably going to go to something like every other one is in person.
Yeah.
Once we can find a corporate sponsor that wants to host.
Yeah, it's going to be kind of hard to hybrid it. I mean, I think it will work, but I don't know what to plan for a space. You could have like 5 people that want to show up live and 20 people that want to be online or something. So, we'll just go to my living room or something. But yeah, I'll please let me know if there's anything I can, put me on the list for organizing or whatever we need to do to keep this going. I'm a big fan, and I just fiddle with research all the time. So like most of us, I think.
Yeah, and I'll repeat, there's a link to the Discord in the meeting description on Meetup.
Oh, okay.
And there is a channel in the Papers We Love Discord that is named San Francisco. So the planning discussions should happen in that channel. And if you would like to be notified of them and have Discord open on your computer for other reasons, then I would encourage you to turn on notifications on that channel.
Well, that's a good reason to have it on then.
So. Yeah. I will say from our experience in Seattle has been you get more attendance at an in-person event than you do at a remote one, which feels paradoxical, but It's
I
true.
started going to the live meetings just a few weeks ago, really. I had been working on I got laid off, so I had time to look around and go places, and I ran into a guy I worked with at Zynga like 10 years ago, on Tuesday. He happened to show up out of like 10 people at this meetup or streaming data thing or whatever it was. And, we just talked, hooked up again. So yeah, there's a lot of, opportunity there for people to, socialize, and you don't always want to stand up and present things, but you can chit chat and, bug people or whatever you want to do.
That's why you need the WiscKey paper, because when you get laid off and you're writing your own database in your spare time, you know how.
Don't get me started. Yeah.
And then, yeah, I guess our main constraint here has been people who are willing to give a presentation about a paper. So that's
Yeah.
the
I got
the
a
easy way
few,
to help is put
yeah.
your hand up and say, I will talk about this paper on this date.
Yeah, and those mini presentations too are a great kind of warm up. And you can just, I don't think what were the rules for that? I think you could just, was it an actual paper or you could just chitter chatter about stuff? I don't know. I think it was a little looser though, like if you're
Yeah, the
working on
minis are
stuff.
supposed to be 15 minutes and the longs are
Yeah.
45.
Yeah.
So it's usually pretty easy to prepare a mini.
Yeah. And I remember,
Also, typically the long paper people would make slides for. A lot of the mini papers, people would literally just share their screen with the paper and scroll through and talk about each
yeah,
diagram,
exactly. No effort needed.
which is the appropriate amount of work for the mini.
Yeah, it's almost like
Yep.
you should read this, not like, this is what it's all about. I think because, there's stuff I'm reading that I'm halfway through and not up on. I do remember a funny trivia thing is like 2019 or something like that. It had to be 2018 or 2017. There was one at Microsoft, and I happened to watch some random video about HLLs, hyperlog log. And at the end of this video, some guy asked a question, and I realized it was me because I was at that meetup. And I asked something about merging. You didn't mention this thing or whatever. And as coincidence had it, I spent like the next couple of years working with HLLs and like building a big estimation system and kind of trying all these data sketchy things. So it was just kind of funny to like remember, did I learn about that back then? So I guess, so yeah, it's funny. It's a fun thing.
Yes, sometimes that can be painful. I gave a Papers We Love talk on distributed hash tables. And someone asked a question that was basically, when I'm writing code, I'm always having this trade-off of, do I want to use a hash table or do I want to use a B tree? So what is the analogy there that if I'm choosing between a distributed hash table, like where's my distributed B tree? Like what's in that box?
Yeah, I know. What's the ordered structure?
And I listen to that question now and it's like, oh, I want to go back and give that answer again.
Yeah, I know. Well, somebody will look it up. It's not, I'm sure he didn't just take your answer as the final, state of what's possible. But yeah, I'd like to look, I'll at least want to keep in touch. So yeah, I'll get on Discord. That sounds great. And anybody else, I guess.
Yeah, and keep in mind, it doesn't all have to be databases all the time. One of the most popular talks that was given at the GitHub location was someone who gave an economics paper on why is it if you have a economy that contains some automatable things and some non-automatable things, you're going to get very different inflation models because the automatable things get amortized better and better and better and better, and the non-automatable things don't. So you get this weird Amdahl's law of your economy. And it's this paper from like the 30s that's talking about the fact that by 1990, healthcare is going to be 20% of our entire economy because you just can automate the things that nurses do. And then you look at the predictions 50 years later, and it's like, music's going to cost nothing and healthcare is going to be super expensive, as opposed to now where healthcare is cheap and music is expensive. And you're like,
Oh yeah, that's good.
And it's just this great talk from a paper from the 30s. And
Right. Yeah, there's some good stuff. Also looking around too.
so yeah, I mean, we accept both ends. If you want to be like, here's a paper on attention and large language models that came out an hour before the meeting started. And someone else is going to be like, here is a paper from the 30s written by Alan Turing about the potential of computers. Ironically, also about large language models.
Yeah, I tried to trace something back the other day, and I ended up back in like 1800. Like it was apparently the least squares method. There was some. I found this. I was looking for like inverse variance weighting, and there's this paper recently, like just 5 years ago or 6 years ago, that says I couldn't find any proof of this. So I started looking around. I even asked like on Reddit, like, is that true? There's no proof of inverse variance weighting. And then people said, no, we did this exercise, all this stuff. But I traced back, I found some texts, from like 1932 where they first started to mention it. And then it went back to, Gauss, and it was just really a special case of the normal equations, but I just needed my memory jog to recognize like, oh yeah, that's a really simple kind of solution or whatever. And nobody ever called it that, they just came up with a new name. And you couldn't find searches, and they just
every once in a while you stumble across those really old citations. You're in the middle of reading something and they're like,
following Gauss
and
in
Charles Boole, this monastery monk who is talking about everything is either true or not true, so that we can boil everything down to a series of truths and not truths. And you're like, oh, Boolean logic, right?
Yeah, exactly. Yeah.
I saw.
I was thinking, because I was trying to trace back some stuff I was working on. I was like, this is very similar to this, but I don't know what to call it, or what, can I find variations and stuff? And I think I'm just gonna call it like least squares. It's like, oh, from Gauss, or from 1800 something. It's not that much different, just a like Euclidean distance kind of thing.
I saw one recently where, yeah, like someone, I think it was in like a healthcare setting, they like invented this new method to calculate the area under a curve, and like published a paper about this new method that they had discovered. And it is now like, it is in their field, like the canonical citation for how to do this thing. And you read it, and
that's
you're
what
like,
I found with
that's calculus. You invented calculus.
Yeah, exactly. With inverse variance, there's all these. I found hundreds of papers that say we use this meta-analysis method to combine a bunch of random stuff, like in healthcare or whatever. And here it is. And I'm like, okay, but where's the site? Where did you get that? Who, And yeah, like I said, I finally had to do like a textbook search, and there was some mention of like 1932 Burge in the physics department at Berkeley. And he had actually done that with physical constants. He had a bunch of random ones with different variances, and he put them all together and got like the speed of light or whatever it was, like Planck or something. And he had referenced something back in 1890 something, and it was something called totally different, just normal equations of some kind of thing. And
Yeah.
instead of a matrix, they just have a big list of equations, whatever. So that was
And there's
fun.
some things that are younger than you think. A lot of those statistical methods you look at, and it's like, this was invented in 1850. And you're like, wait a second.
It is.
Deciles were invented in 1850?
Yeah.
Like mean, median, and mode are not mentioned in Newton's Principia Mathematica, because when he was doing calculus, no one had thought of averaging yet.
Well, yeah, in fact, the stuff I was reading was about how to, well, first they had to establish that you could combine measurements with error, like the variance could be kind of correct, and that was actually what the book was about. And then they mentioned, well, the optimal version of this is, blah, 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 do this, which is now the canonical method for everything. And it goes back to Gauss too, because he kind of solved it in general. And it's really like there's kind of a perpendicular normal vector that goes to the cloud of data points that you're looking at, and you kind of find the closest solution. And, you know, that's like inverse, that's least squares method. That's like, you know, but it's really easy geometry, but sometimes it gets kind of out of hand. I think there's some things that are really hard to solve. So, you know, but he came up with a very general method of like, you know, it's basically at a perpendicular, and if you go left or right, it's farther away, you know, so it's minimal distance. And that goes back to Gauss or Legendre, I think. So
yeah, Hamming, who did the Hamming error correction codes,
right,
also has a bunch of codes he published, and he's like, these are provably optimal codes. They take exponential time to decode. And you're like, thanks. I'm gonna go use the Hamming codes that are not optimal, but are in linear time.
Yeah, exactly. Well, they're optimal in consuming compute resource.
I mean, he put his name on the right one.
Yeah.
You've got to someone, and they're like, I have two methods.
Everybody's like, don't do this, don't do this.
This one is complicated, and this one I have literally named after myself. You know which one they want you to use.
Yeah, I think it's true. Like if they named it after you, that's the one they like, you know, like something, all the good stuff you thought was really cool, and you know, pigeonhole somewhere.
But yeah, and then how does that shift over time, as you know, to the point of,
Yeah.
oh, like when you did that, perhaps space, you know, storage was very expensive and compute was relatively cheap. So like maybe it made sense to do the more computationally expensive one to really optimally encode that stuff. Whereas now like storage is stupid cheap and compute is relatively more expensive. And so, yeah, obviously use the slightly less optimal encoding.
Right. It constantly changes.
So speaking as someone at a startup that has gone full remote and assigning work to other people, who here has connections at a company that has a big room that is in San Francisco?
Yeah, because you know, like I said, I was at this. I think GitHub we could ask, because they were having like this AI meetup or AI camp or something like that. It was the same, you know.
Yeah, so we've done more at GitHub than anywhere else.
Exactly. Yeah, it was a very similar setup.
We've done a bunch of them at Akamai.
You know, and a projector. I think they do them every night or almost, because like nobody's in that office now, and they're just using it for events. So, you know, and I went to two. Like that one was last week or the week before, anyway. And then another one at a place that actually had a real office on 2nd Street. Lenses.io, lens stuff. But it's like a streaming management kind of nice version of Kafka.
Okay, so I'll call GitHub and say, remember 6 years ago when you said call anytime? This is a time.
Yeah, just keep going. And they just rented it, I think, this year though. So, but there, you know, there's a few little spaces that it was maybe room for 10 people, like I said, but not a big auditorium. But they were happy to have us over, and I think maybe not anymore.
Well, if history is any guide, it starts small, and the more reliably you do it every month, the more it snowballs. There might be
some. I was thinking, like, you know,
you just have to make a habit of people check because they know that every second Thursday of the month is a meeting.
And if you're desperate, like there's non-tech spaces that are like 90% empty, you know, like down the street, there's a public room on Haight, and there's a, because you know, I go to community meetings too, like there's all kinds of empty like community centers and things where you could sign up maybe or talk to somebody. You get like room for hundreds of people if you want on some nights, you know, on a Tuesday night or something. So yeah, but yeah, I think yeah, I'll keep my eyes open. I'm gonna keep going. I am just getting out. Like I said, I like schmoozing with people, and it's better than sitting at home. So I'm gonna be, you'll see me stalking you on the street somewhere.
No, it's true. The longer and deeper I work with computers, the more I'm convinced I like humans. I'm gonna go talk to a human now.
yeah, exactly. I can't think of anything I want to do with a computer right now. I need to interact with people before I get really excited about doing anything. So, yeah, I've got plenty of time. I'm getting nothing done at home right now. So, any.
Now we just
but,
need to convince some academic to do a academic study on the number of startups that came out of papers we love, and then present it at papers we love.
Exactly. Papers we love about ourselves. Yeah, but yeah, I will try to I do want to have the real, in live or hybrid kind of venue. And I think for instance, I'm not even sure if if these places, I think most of these places are set up where they expect a lot of people to be off, online or whatever, or out of the building as well. So remote or whatever you want to call it, to those presentations. So I think
All
that
right.
would work, so.
On that note, I will thank our speaker one more time, and then we'll stop the recording.
Yeah.
Thank you.